All right, I'm going to start. So, welcome everybody. I see a lot of people that I know, a lot of new faces. So this is Study Union, and this is for Computer Science 1 in case anybody's lost. And yeah, I'm basically, so I had the review sheet. If anybody who needs the review sheet, it's on the website, which is the ucfsarc.wordpress.com/cop3502. The review sheet that I'm going to be using is on there, so you could either look it up online, write your notes like on your own pages, on your own papers or whatever. Yeah, it will be recorded for those. I mean, most likely, for the most part, it's probably going to be the .cam. But anybody that that's just like a warning, or not warning, but a disclaimer, just in case anybody is not comfortable with that. And yeah, for the most part, I'm going to try to make it. Since it's a lot more people in different sections, and it's also live streamed, so it's not going to be as interactive as my usual sessions. But I'll sort of try to make it like as interactive as possible. And there's a lot of material, so let's go through it. Also, whoever downloaded the worksheet, like, what's up?
Will there be like a section of us asking questions, or just?
Yeah. The last 15 minutes, I'm going to leave it like for questions. Yeah. But for the most part, I'm just going to try to like go through the entire worksheet because it's a lot. So, yeah. So if you download the worksheet like with it like more than half an hour ago, I did make a couple changes and just uploaded it because I realized a couple like mistakes. So I will let you know if there are any changes, or if there are any changes from what you see like on the screen, then like don't worry, just write the changes in. Yeah. All right, I think let's get started. Now, so we have the table of contents. I'm basically going to go over the final material. There are tries, heaps, hash tables, some math stuff, and backtracking. And just in case, like depending on when we finish this, I mean, I doubt we'll be extra with time. There is like a merge sort recurrence relation just in case. And it's probably not going to be on the exam just because it's not. You guys have already been tested on that, but it's not. It's always good to know. Now, so back into tries. So for tries, the data structure, how the data structure works for a try is that it's basically like your normal binary tree. But a normal binary tree has 2 children. A try has 26 children, 1 for each letter of the alphabet. And a try is just basically it's not memory efficient, but it's really time-wise efficient to store a corpus of data. And for those with Dr. Zimlansky, you should know what the word corpus means, just because he kind of like emphasized that, which is a body of text. And what was the other one? Lexicon. Lexicon is just a group of words. Okay. So the runtimes for tries is that if you start your tries, you have your insertion. Then the best case runtime for insertion in a try is what? Shout it out. Order K. And what's K? Yeah, so that's order K, and that's why I kind of like left this space at the bottom. You could write like where K is length of the string. Is the length of the string. And then average for insertion into try is also order K. And then worst case is also order K. Because there's really no early terminating condition for insertion. For insertion, you just go through each letter. You go through each letter in your string, and then you insert it one by one into the try. There's no early terminating condition. There's no, yeah, and assuming like your try is really large, and because you can't assume that it's null. If it's null, then yeah, it might have a null check, which would make it order 1. But that's wrong because you never assume that your try is small. Okay, searching. Best case runtime for searching is what? Shout it out. Order 1, and when is that? When the word doesn't exist in your try. So like, let's say, for example, not only, that's actually not really a good explanation, because you could have the word banana in your try, but if bananas is not in your try, it's still going to traverse most of the word bananas. So the explanation that it's not in your try is not really a good one. So yeah, that's a much better explanation, where the first letter of the word that you're searching for is not in your try. So for example, if your try has like all the words in the world that start with the letter A, and then you want to insert the word cat, you're automatically going to look for the letter C, and it's not going to be in your try. So that's when you stop right away. So yeah, best case is order 1. And then average is going to be order k, because assuming you have like a really large try, it's going to have a lot of words. So most of the time it's going to traverse most of the word. And then worst case is also order k. Deletion, what's best case for deletion? Shout it out. Order 1. And it's basically the exact same explanation for searching. Usually searching, the runtime for searching and deletion, they're kind of like go hand in hand. They're very similar because you can't really delete without searching first. Whenever you delete anything, you have to search for it first. Yeah, so best case is order 1. And then average is order k. And then worst is also order k. So the next question is just write a simple try node for a try node struct in C. So what's in the try? You're gonna have basically your 2 data members, or what are those? Yeah, an integer. What does an integer hold? Yes, so you're going to have your int count, so you're basically going to have your normal syntax. You're going to have type def, or here we don't even have to type def, so you could just say struct. Try node, and then you're going to open your parentheses, and then int count, and then what's the other member? Yeah, so struct, that's really important to have the word struct, because the word well, first of all, we did type def anyways, so yeah, so the word struct in there is really important. So struct, and then try node, and then they're pointers to try nodes, so you're going to have to say star children, and then how many children are we going to have? 26 children. So the next question I kind of like was really like excited. 10 lines, I think that's a little too much. Maybe 15. So I'll first of all like erase the 10 and write 15, because 10 is a little cutting it. Like you might have to like make some sacrifices. So, but 15 is definitely a lot better. So if you just have your typical insertion function, you're going to have your void. Let's make it a void function. So void, and then insert. Then you're going to have your try node as a parameter, try node root, star root, and then your char star string, which is what you're going to insert. And then you're going to start your function. So I'm not going to do a null check just because it's going to take some time and space, and I didn't put enough space for this question. So yes, but ideally you should put like a null check here for your root. Null check. But then you're also going to need int. You're going to need int n, and then the n we're going to find out what the string length is. So we're going to call strlen, and then we're going to pass it in the string that was passed in as a parameter. And then we're also going to need some kind of counter for a for loop soon. So we're going to also say I is equal to 0. So because the way that insertion and try works is that you basically have a for loop, and then you start at the first letter of your string, and then you keep on traversing the try for that letter. So if you're inserting the word dog, you go to D. So that means you're going to go to the D child of your root, and then you're going to keep on going to the O and to the G. So what happens if the D child doesn't exist, or it's null? What do you do then? You create it, and then it's basically the whole wizard analogy that he has. You create it, and then you jump onto the platform. Every time you see a child that doesn't exist, you create it first and then jump on. So it's basically going to be a for loop. So it's going to be for I is equal to 0, I is less than n, I plus plus, and then we're going to say if root children. So we're going to go to the children array, and which child are we going to go to? We're going to use the ASCII value of the letter. So we're going to say str sub I. We're going to use the ASCII value of the letter, and then what are we going to subtract from it then? The letter A, because so if we just think of it this way, so if we're inserting the word apple, and we want to start with the A, so A is going to be the zeroth child of your root. So you want to do A minus the ASCII value of A, so A minus A will give you 0, and then B will be 1, and so on and so forth. So you're going to subtract A. So yeah, we're going to check that if it's equal to null. Then we're basically going to create So what you basically what you should do is that you should write root, and then child, and then blah blah. The same thing. Say it's equal to create node. We're going to create a node. Yeah, so it's gonna when like these dots are basically indicating that's the same thing as above, whatever that is. Just write that, and then say it's equal to create node. So we're gonna create a node, and then after creating the node, we're actually gonna jump on it. So we're gonna say So since it's a function, we can't technically change the value of root because we're not gonna be changing back at main. As long as we don't dereference root, we're good. So we could say root is equal to root child. Or children, sorry. Then the same thing we're going to do is stri minus a yeah, that's it. Okay. So then once we do that for an entire string, and then we just do count plus plus, or yeah, count plus plus, or sorry, root count plus plus. Plus plus, and then we're done. So yeah, that's basically just a very simple insertion into try node, insertion into a try. All right. So, all right. We're gonna initialize what? Well, so we're going to assume that create node does that. So the question was that do we initialize count equals 0? And the answer to that is we're going to assume that create node does that for us. What's up, Noah? For what? What about it? Oh yeah, yeah. Oh yeah. Actually, this is So this is not yeah. Okay, good catch. So I completely forgot. I got a little excited. So yeah, you should definitely close your parentheses, and then semicolon. So you could also write try node, but that's kind of like optional. You could write try node over here. Even when you type that thing, it's still optional, but it's still good practice to write that there. Sorry? This? Yeah, so it is dashes. So it is because it is dashes just because it's indicating whatever, it's the same thing as whatever's on top of it. And I didn't feel like writing that whole thing. Okay. So yeah, it is dashes. Now, so next question is, I wrote this weird try, and I made it really weird for two reasons. A, for space economy, because I didn't want to put the word banana and take up the whole page. And B, I just wanted to try throw you off somehow, and this was the best thing I came up with. So what's wrong with this try? Well, it's beautiful. It's a majestic try. What are you talking about? So what Ben said is that there's a count in the root. Is that a problem? Yeah, so that comes. I will have that question later on. It does represent the empty string, so that's not really a problem.
It doesn't go all the way down. It tries to trick you.
As I said, it does. So in your computer, a try doesn't really have a shape. So it's not. So the shape and the visual shouldn't really throw you off at all. What's that? Yeah. Yeah, okay, so that's what I was trying to get to. So if you look at the word zoom at the very right, the Z, and you go down and traverse the whole thing, it's just a bunch of zeros. So if this were a properly coded up try, that should never happen. If it's a bunch of zeros, what should you do right at that point? Just delete it, just get rid of it. So yeah, so that's kind of what's wrong with this try. So zoom has a count of 0, delete. So that, yeah. Zoom should be deleted. Should. Deleted, yeah. So the way I'm going to represent deletions, I'm just going to put a cross over the nodes. So that should be, all right. So this is also kind of a change where I wanted to do, but I completely forgot. So change this question to how many unique words. So how many unique words are represented in this try? Okay, so unique word. Okay, so also change this to a string. Unique strings. Because the empty string is technically considered a string. But I don't, whether it's considered a word or not, that's, yeah, whether it's considered a word or not, I think that's like a philosophical debate. So
A word is more than one letter, right?
I think I would also argue that, so we're not getting into that, so which is why strings. And the empty string is considered as a string. Okay. So 7? How do you guys get 7? So we have one empty root, and then we have, so 1, 2, 3, 4, 5, 6, 7. Okay, I honestly didn't count, so I didn't know what was the answer. Okay, so yeah, that's why I add the word unique. So the word unique, the fact that you don't count for repetitions. So since it's unique, we're not gonna. So A are all the same word. They're not really unique. You only have one unique A. So yeah, the answer's 7. And what are those words? We have. Yeah, so we have the string A, we have the string ape, and then we have the string app, and then we have the string ban, and then we have the string banana, and then we have the string I. So, yeah, next question is about deletion in a try. So if we wanted to delete the word ape, how would that look like? So what would we do then? If we want to delete like one instance of the word ape. Yeah, so we want to traverse all the way down to the word ape. So we start the empty the root, and then we go to the A, and then we go down to the P, and then down to the E. So then we're going to just decrement the count. So it's a 2. So the 2 becomes a 1. So if we want to delete the word banana, so you go basically the whole thing, you go B-A-N-A-N-A, and then there's a 1, and so then you would decrement the 1, and that becomes a 0. So now that it became a 0, that means that there's really no use for it. But before deletion, or what was I going to say? Yeah, so once it has a 0, you start getting rid of it. And you also want to check. Here, actually, so here, before deleting banana, let's delete like an instance of ban, just to show, because I just realized I didn't include this case. So if we delete ban twice, let's delete twice, just because. Anyways, let's just delete this twice. So if we delete ban twice, this becomes a 0. So since this became a 0, do we delete the rest? Do we delete the whole string? No, because it has children. So you only want to delete if it doesn't have any children. So now that we delete banana, so now this has a 0. So then you're going to cross, it has a 0, and then this node over here doesn't have any children. So you're going to cross that out, and then you're going to keep on crossing out until you hit a node until you hit a node that either has a count or has some other child. So yeah, you're going to keep on deleting. So in this case, we delete the ban, so this is going to keep on deleting until the root, which has other children, has the A, the I, the Z, and all that. So the last string is that if we delete I, this basically turns down into a 0, and then that's also deleted. And then, yeah, so what's left is that we have the word app, the word A. That's basically it. Okay. So so we did deletions, and then what does the I in the string in the try node? What does the 1 at the root of the try represent? The empty string, yes. Okay, so I think we're done with tries. Okay, on to heaps. Yeah, what's up?
Well, when there's a 1 at the root of that try, does that mean that there's an empty string inserted into the try?
Yes. Yeah, so the question was that if there's a 1 at the root of the try, that means that somehow an empty string ended up being inserted into the try. And how that ended up, let's not worry about that. But the fact is that means that there's an empty string in that try. So going on to heaps. So the general idea behind heaps is that you always want to be able to have an order 1 access to the minimum of your array or data, whatever data you have. So the way that we do that is that so the whole plot twist behind heaps is that they look like, so the way we represent them is through trees, but really they're actually arrays the way we code them up. So the way that heaps work is that you always have your minimum or max, if it's a mini heap or a max heap, you always have your min or max at your root. Okay, yeah. So insertion. So insertion into heap. What's the best case runtime for that? Order what? Order 1. Yeah. So best case is order 1, where if you like, let's say if you have a heap, and the maximum, if it's a min heap, and the max of that heap is, like, let's say 100, and if you insert 150, that 150 is going to stay at the bottom. It's not going to go anywhere. Yeah. So it's order 1 best case. Order 1 average is order log n, because the average is that if you delete something, you're gonna, or if you insert something, it's gonna percolate up to some degree. So it's gonna be log n. And then the worst case is also log n. Yes. Well, yeah. So log n basically represents the height of the tree. And then searching, best case. So searching, this is kind of like a tricky question, because searching in a heap, you only have access to search the root. So if you searching the root is basically an order 1 runtime operation, because you just check the root. There's no math involved, so it's order 1 all around. Deletion is the same. So it's once you delete, you have to delete from your root, and then you go get your bottom rightmost leaf node, and then you replace it with your root, and then you percolate down. So percolating down, that's on average like an order log n. So it's going to be order 1 for best, and then order log n for average, log n, log n. Percolate up, best case is order 1, average is order log n. So it's a bunch of log n's all over. Order. No, bottom right most leaf node for deletion. That's what you get. We'll talk about percolating up, like it'll come. So order 1, order log n, order log n. All right. Where here you could write whatever notes you want. Here n is the number or the length of the array, since heaps are actually arrays, the length of the array. So heaps have a bunch of properties. What's the structural property of a heap? A complete what? A complete binary tree, yes. So that's basically the structural property. So a complete binary tree. A binary tree. And then what's the ordering property of a heap? So let's talk about min heaps for now. Let's assume it's a min heap. If it's a min heap. Yeah, so if it's a min heap, the value at the value of any parent node has to be less than all of its children. Must be less than all children. And then what are the two different types of heaps? Do we have the min heap? We have a min heap and a max heap. And we also have a max heap. And then the difference basically is what? So in a min heap, parent is less than child, or children I should say. And a max heap, the parent is greater than or equal to child, or greater than, yeah, let's just say greater than or equal to child, or children. All right. If you have duplicate values, then, so what do you mean duplicate values? So if you're if you're inserting a value that's already in the tree, or in the heap? Honestly, they're both less than or equal to, so it doesn't really matter. Yeah, so you could change like that. Parent is less than or equal to child. No, less than or equal to, so like if you're percolating up or down, and let's say if the parent is a 4 and your child is a 4, do you percolate up or not? Yeah, you just stay there. You don't do anything. So it's less than or equal to child. It doesn't really matter. Okay. Now, so for heaps, that's it for like the runtimes and just like how heaps work. All right. So next page is. Oh yeah. Wait. I feel like I skipped one. Did I? Oh no, I didn't. Okay. So yeah. So describe the following algorithms when it comes to heaps. So like let's just assume we're working with a min heap, so you could even change this to a min heap. So when we're talking about min heap, so the way that insertion works is that one, you want to preserve completeness of the tree. And then two, insert data. And then three, percolate up. Which we'll talk about percolate up soon, so don't worry. So for deletion is that you're going to delete what's at the root, since you can only delete what's at the root. So one, delete root. Two, replace root. We'll replace the root with whatever. So also in our attempt to preserve the completeness of the tree, we're going to delete our bottom rightmost leaf node, and then put it in place of our new root. So our new root is going to be the bottommost right leaf node. Replace root with bottom rightmost leaf node. And then after that, then percolate down. Percolate down. So searching, this is also kind of like, I mean, it's not really a trick, but it's not really a trick because you guys know what the trick is now. So trick, you can only look at the root. All right. Yeah, you can only look at the root. All right, so heap representation. Here's where we'll talk about like a bunch about percolate stuff. So, oh yeah, I was just saying, yeah, it's just trick. You can only look at the root. Yeah, because so searching implies that you can like search whatever's in your heap, and that's false. You can't do that. That's bad. Just because it'll wreck your runtimes, it'll be kind of useless. It'll destroy the whole objective of a heap. So, yeah, you can only look at the root. You had your what's up? Oh, BRM, bottom rightmost leaf node. Yeah. Which again, like if this doesn't make sense, like we'll do a couple like operations and hopefully it'll make sense like in the next page. Okay, so now we have a bunch of these numbers. We're going to insert it into like starting from scratch. So if we start from scratch, we're going to start with the 45. So we have the 45, and then there's nothing to do there. So next we insert the 23. So what happens here? Yeah, you always percolate up, and then in this case, it's going to swap with this parent. So I'm going to use this double arrow to like indicate percolation, and like this single arrow to represent like a next insertion. So after the percolating, the 23 goes to, because the parent has to be less than the child. So now that's a good heap. So when you want to insert the next number, you always first preserve the completeness of the tree. So in that case, you only have one place that your next number can go in, and that is to the right of 23, to the right child of 23. So yeah, so the next node cannot be the left of 45 or the right of 45. Every number you insert only has one place to go. And in this case, it's going to be the right child 23. So it's going to be 23, 45, and then 84. And then that's a good tree. That's a good heap. So we don't really need to do anything. So next is we're going to do insert 31. So it's going to be 23, 45, 84, and then the next one is going to be over here, which is going to be 31. And then here we're going to percolate. So when you percolate up, you start at whatever you inserted, and then you keep on looking at the parent. If it's a min heap, and in this case the child is less than the parent, then you swap. So you keep on swapping until, so we're going to swap the 31 with the 45, and then we're going to look at the parent again. We're going to look at the 31 and then compare it with its new parent. So 31 is not less than 23, so that's where you stop the percolation. 23, 31, 84, 45. All right. Now next, after 31, we're going to put a 59. So it's going to be 23, 31, 84, 45, 59, and then that's all good. At every node, if you look at every node, the parent is always less than both its children. Okay. Now next we're going to put in the number 2. So it'll be 23, 31, 84, 45, 59, and then to the left of 84 it will be 2. So now 2 is that, again, we're going to, since 2 is less than its parent, we're going to percolate up, and then you compare with its new parent 23, it's also less than 23, so it's going to percolate up all the way to the root. So it'll be 2, 31, and then the 23 would have swapped with the 2, so it's going to go down, 23, 45, 59, and then 84 swapped with the 2, so it's going to be 84 down here. And then 64, so it's going to be, I hope you guys notice the pattern, how you just basically keep on putting on the next right until you fill your layer, and then you start a new layer. Okay, so it'll be 2, 31, 23, 45, 59, 84, and then we inserted 64. So this is still, it's a good min heap, so we're going to keep on going, and then insert our last one, which is 15. So it'll be 2, yeah, I'm going to do this on a new line. So it'll be 2, 31, 23, I'm running out of space. Okay, so 45, and then we inserted 15, and then to the left of 31 it's going to be 59, and to the right is going to be 84, and 64. So right now 15 needs to be percolated up because it's less than its parent. So it's going to percolate up all the way to 31, and then it's going to stop because it's not less than 2. So the new tree is going to look like 2, 15, 23, 45. Oh, sorry, 31. 31 would have swapped here. 31, 59, and then 45. And then here is we have 84 and 64. All right, 84 and 64. So hopefully that's, I mean, I guess I should have put more space, but hopefully it makes it like this over here. I don't think that's too clear. This is the 31 over here. All right, that's 31. All right. So next question is draw a heap that contains, here, let me zoom in a little more. Yeah. Draw a heap that contains at least 16 nodes that will cause an order 1 deletion. So when we're looking for an order 1 deletion, what are we really looking for? Yeah, so we're looking to kind of like minimize percolating down. So the way we do that is that we look for, or we want to construct a heap such that when you delete the node, it's going to be, so because the bottom, so whatever, when you delete a node, the node is going to be at the bottom, the node that's going to replace your root will be at the bottom. So you basically want to be able to take it from the subtree that it's in and put it in the other subtree. So yeah, so we'll talk about this. So you basically, so if you really think about it, there are only like 5 nodes of interest that we're actually interested in. So since the question was at least 16, I'm going to choose exactly 16 just because there's no reason to overachieve. So you start at the root. So the root is definitely, I mean, the root is kind of one of the nodes in interest, and then we're definitely going to be interested in both of its children. And then, so since we have 16 nodes, the bottom rightmost leaf node will be in the left subtree. So since it's in the left subtree, we're going to be interested in trying to send it to the right subtree. So since we're going to be sending it to the right subtree, that means that these 2 nodes are going to be important for us. And then that's it. The rest don't really matter. So then you could just keep on inserting like dummy values. And then, so this is 8, yeah. So yeah, so it's like that. And then, all right, so this is like kind of 16 nodes. So let's say, so since it's a min heap, it's always like a good idea just to start with like 1 as your root. So like this is just 1. and then like let's put like 50 here. So whatever's going to take its place is 50. So 50 is in the left subtree. So since 50 is in this left subtree, what values can like this node take? Sorry? Yeah, greater than 1, less than 50. So let's not worry about duplicates. So this node can only be greater than 1, less than 50. So let's say it's 30. So since it's in the left subtree, the 50 is in the left subtree that we're going to delete, and we want to send it to the other side. What value does this node have to be? Sorry? Yeah, it has to be between 1 and 30. So it has to be between 1 and, we want it strictly less than 30 because when we put the 50 here, it's going to percolate down. And which one do we always swap with? We always swap with the lesser child or the smaller child. So if we swap with the smaller child, we want it to swap with the right child. And in this case, for it to swap with the right child, it has to be less than the left. So let's just say this is like 20. So to cause an order 1 deletion, we want to be able to put the 50 on this side, and then we want it to stop here. So what values must these two nodes be? Yeah, they must be greater than 50, because if we want to stop percolation, the parent has to be greater than. Oh, sorry, the parent has to be less than his two children. So let's put I put a small circle here. So let's do like that. Let's put like 60 and then 70. 60 and then 70, and then really the rest of the tree you could just fill it up with whatever values you want. So let's put just 31 here, 32, 33, 34. 35, 36, and then here this has to be greater than 60, so let's say 61, 62, this has to be greater than 70, 71, 72. And then, so a deletion right now will cause an order 1 deletion, because if you delete the root, this goes away, and then we get the bottom rightmost leaf node, which you go to the bottommost layer, and then you pick the rightmost leaf node, and in this case it's just the 50 by itself. So the 50 is going to take its place, and this is going to go away. The 50 is going to take its place. And then, when it percolates down, it's going to swap with the smaller child, which is a 20. And then 20 takes its place. So 20, and then the 50 goes down here, which is now 50 is now here. And then it just stops because the 60 and the 70 stop it. Yeah, what's up?
Why do you need like 30 or 20? Like, what if everything was greater than 50 to begin with, it would never even have to percolate down once, right?
Well, if everything was greater than 50 to begin with, then the 50 wouldn't have been there to begin with. Exactly. So this strictly has to be less than 30, less than 50. Okay, and yeah, what's up?
So no matter what, when you delete, you have to percolate down no matter what.
You have to percolate down at least 1 level, at least, because as I said, so it wouldn't have been in the tree that it is. Yeah, because if it's at the very bottom, then that means it's going to be relatively big. But the point is, you kind of like want to bait and switch into the other subtree. Okay. So now the next one is draw the array representation of the heap that we just drew, and I kind of like drew all over it. So hopefully, maybe we can like uncover information from it. So how does the array representation of a heap look like? So if we draw, so first of all, we have 16, so we're gonna need 16 spaces in our array. So it's gonna look something like this. Is it on? Yeah. Okay. Here, I'm gonna move up. It's gonna look something like this, and let's do like 1, 2, 3, 4, 7, 8, 9, 10, 11. 12, 13, 14, 15. Okay. So right now, if we want to put the array or the heap that we just drew into an array, we basically just start at the root, and then we will keep on working our way from left to right. So this was originally a 1. So there was originally a 1 over here, and then the left was a 30. The right was a 20, and then so you go from bottom. You start from the top, and you work your way left to right. So we did 1. 30, 20, and then 31, 32, 31, 32, and then 60, 70, and then 33, 34, 35, 36, 35, 36, and then 61, 62, 71, 72, 72, and then 50. I guess I drew one extra. 50. So that's what it looks like in an array. Because heaps are actually arrays, so it's important to know that. What? I would say top to bottom, left to right. So yeah. So you stop top first and then left to right each layer. All right, I think we're done with this page.
For that array,
What about this array?
for that array, you don't include the 0th index, right? You start at the first index. I mean, at index number 1.
What do you mean you start index number 1?
I've seen some people do ignore the 0 index, and then they start at the 1 because the left child of whatever index node you're at is going to be like 2 times.
Oh, I think that's Dr. Mead's style. I know Dr. Mead, he does like 1 indexing sometimes, right?
I don't know Dr. Mead. I don't have Dr. Mead. But
So where do you hear that from? Just out of curiosity.
just like online and GTAs.
Yeah.
It makes sense because like if you have the root as your 0 as index 0, if you do 2 times 0, then it's still 0. So that's why like you just ignore the.
No, but you do 2 times 0, then you add 1 and 2. Anyway, so just I won't worry too much about that. So we'll get to that. I think what's the next page? Oh no, heap sort. Okay, so yeah, we'll get there. So yeah, so there's 0 indexing or 1 indexing. I know Dr. Mead, he does one indexing sometimes. He talked about that, I'm pretty sure, at some point. But for Dr. Zimnowski, just start at 0 always. Okay? It's just different it's just different styles. At the end, like there's no better end result. It's just different styles. So I don't think there's any one that's better than the other.
But you just have to be consistent.
Exactly. You just have to be consistent. So heap sort. What's the runtime for Heapify? Best case, average, worst. They're all kind of the same. Where Heapify is basically just take an array and then you make it into a heap. Because if you look at the array that we just wrote last time, you look at this array. Where is it? If you look at this array, it's not really sorted because you go 1, 30, 20, and then it's not sorted at all, but it is a heap. So that's kind of like the important distinction between making it a heap and actually sorting it. So it's kind of like a one conditional array where a sorted array is always a heap, but a heap is not always a sorted array. Okay, so yeah, just make that distinction. So if we call Heapify, the function Heapify basically just takes an array and makes it into a heap. It doesn't necessarily have to be sorted. So the runtime for Heapify is just, you could, technically it looks like an order n log n, but it's actually kind of like, if you do some math, it's actually order n. So, but both answers are kind of like acceptable. So it's actually an order n or n log n. The thing is, so mathematically it is actually just order n. So the only reason why I say or n log n is just because I don't think any of your professors want you to expect you to kind of like know the math proof behind it. So I'm pretty sure they would accept either, accept either answers, where n log n or order n, because getting the order n is very mathy, and so it's kind of like a proof behind it. What's up?
Is it because like you use a sorting algorithm, like you can use the merge sort or different sorting algorithm? That's why is it order n or order n?
No, order n is so Heapify is not a sorting algorithm. That's kind of like what I was trying to get to. Heapify is not a sorting algorithm. It's making an array into a heap. It's part of heap sort. So the first part of your heap sort you want to call Heapify. But the reason why it's order n, as I said, some math proof that you don't really have to know, and I don't really have it memorized off the top of my head. And yeah, so I would double check what your professor wants you to say.
What does Heapify really do? Like, does it?
Heapify would take an array, which we're kind of going to actually get, that's kind of like a question here. So we'll do it. It'll, hopefully it'll make sense like in a little. So yeah, I'll definitely double check with your professor. In my opinion, would say they should accept either answer. But the mathematically correct is the order n. So maybe that's kind of like the more safe answer to go with. Anyways, so yeah, let's just say order n for now. Order n, and then heap sort on average is n log n. Order n log n. N log n. All right. So, and here, so the next question, what's the difference between Heapify and heap sort? So Heapify makes Heapify converts into a heap. Converts array into heap. And then heap sort actually sorts the array. How does it sort the array? So the way that heap sort works is that you make it into heap, and then if you want to sort that array, what's the property of a min heap that we have? What's the property of a min heap? Like, what do we know that's always at the root? The min. So if you just keep on deleting the minimum, then you will eventually have. If you just keep on deleting the minimum and put it into like an auxiliary array, then you will eventually have a sorted array. So you just keep on deleting from your heap until you end up with an empty heap, and then you're done. Then it's sorted. For max heap, it's the same, but you're gonna have to fill your array in reverse order. You're gonna have to start filling your array from like the right to left instead of left to right, because it gives you the max. So you want to put the max at your right.
Where does the log n come from for the heap sort?
Log n? Yeah. So the log n part comes from the percolation, because you're gonna percolate. So every time you delete something, you're gonna put your bottom right most leaf node, put it on top, and then percolate down. And percolating down is a log n operation. So if you do n log n operations, then it would be n log n. If you do a log n operation n times, it's n log n. So Heapify is so the way that Heapify works is that you start at the bottom right most on leaf node. The bottom, okay, I'm going to write this one out. Bottom, right, most. This time it's non-leaf node. Non-leaf node, and then call percolate up. And then call percolate up. And then here, and so the bottom right most non-leaf node is an easy one to get. It's just because it's the parent of your last leaf node. Parent of last leaf node, and then call percolate. Percolate down, not up. And then describe heap sort. Heap sort is just taking a heap, and repeatedly deleting min until the heap is empty. Deleting min until heap is empty. All right, so we're kind of spending a little too much time on heaps, so I kind of going to move on next to hash tables. So we'll just do this question real quick, where here we have an array of, here we have an array of length. So it's going to be 1, 2, 3, 4, 5, 6. Oh yeah, so this is one of the changes that I made with the last, because I kind of mentioned a couple changes. I just changed the numbers because I had way too many 4s. I didn't realize that. And so this is just like new numbers, where it's 12, 25, 4, 8, 36, 22, 45, 14, 18, 89, 2. Now, so if you want to heapify this, what you want to do is that, so if we just kind of what you want to do is that you want to start, so here you have a couple of equations where if you want to get a parent, the equation of a parent is I minus 1 over 2. The equation of the left child is 2i plus 1. The equation of the right child is 2i plus, sorry? Okay, yeah. 2i plus 1, and the right child is 2i plus 2. So if we want to start, we're going to call, we're going to start at the end. We're going to start over here, and then we're going to find the parent of this node. So the index of this array is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we call the parent of this is going to be 9 minus 1, which is 8, divided by 2 is 4. So it's going to be 0, 1, 2, 3, 4. So we're going to look at this 36, and we're going to call percolate down. So percolate down is going to look at both of his children, and it's going to swap if necessary. So the children of index 4 is 2i plus 1 and 2i plus 2. So if we're looking at 4, 2i plus 1 is 9, 2i plus 2 is 10. So it doesn't really, and since the array ends at 9, so it doesn't really have a right child. So it just has a left child. And 36 is less than 2. So if you look at 36, it is less than 2, so it's going to swap. So your array after calling down percolate, after call percolate down on the 36 is going to look like this. So it's going to have 1, 2, 3, 7, 8, 9. So it's going to be 12, 25, 4, 8, and then the 2 is going to swap to 36, 2, because 36 is greater than 2. And then 22, 45, 14, 89, 2. 89, and sorry, then 36, because it's swapped. So we called percolate down on the fourth one. Now we're going to call so since we got the bottom rightmost non-leaf node, we're going to start percolating down left, like going left. So we started here, we started at the 2, and then now we're going to go do it at 8. So 8 is index 3. The children of index 3 is 3 times 2 plus 1, which is 7, and 3 times 2 plus 2, which is 8. So you're going to look at the 8, you're going to compare it with index 7 and 8, which is the 9, which is the 4 and 89. Which one is the 8 going to swap with? It's going to swap with the lesser child. So the children of 8 is 4 and 89, so it's going to swap with whichever one is smaller. So it's going to swap with the 4. Oh, is that 14? Oh, okay, 14. I guess I don't know my own numbers. Anyways, so yeah, it's still going to swap with the 14 because 14 is a lot less than 89. So these two are going to swap, and then it's going to look it's going to be 12, 25, 4. It's going to swap with the 14, 14, 2, 22, 45. Now 8 swap, sorry. Wait, oh no, what did I just say? No, it's okay. Yeah, okay, so it's a min heap, yes. Okay, so, oh man, I kind of, yes, it wouldn't swap. Okay, sorry, I completely messed, I messed up a little. Yes. Okay, so 8, you don't automatically swap with whichever the smaller child. You first have to check if they're both smaller than the root. Okay, so yeah, so you check with 8. 8 is both smaller than the 14 and the 89, so it wouldn't swap to begin with. So that's kind of like the mistake that I did. Don't make that mistake on the exam. So yeah, so the 8 stays here, and then this is 14, and this is 89, and then 36. So we called percolate down on the 8. Now let's call percolate down on the 4. 4 is index 2, so its child is going to be index 4 and index 5 and 6. So we're going to look 0, 1, 2, 3, 4, 5, and 6. The 4 is also less than both of its children, so it's not going to do anything. So we're going to call percolate down 25. The children of 25 is 3 and 4, so it's going to look at the 8 and the 2. It's going to swap with the 2. So 2 is going to be here, 25 is going to be here. And then 12 is going to swap with, it's going to look at the 2 and the 4, is going to swap with the smaller one. So your final array is going to look like this. So we swapped the 12 with the 2, so it's going to be 2, 12, 4, 8, 25, 22, 45, 14, 89, 36. Now, notice how it's not sorted, but it is a heap now, because if you look at any point, if you look at any point, the two children are always less than, the parent is always less than both the children. All right. Oh, here. All right. Sorry if it's going a little fast, but that kind of took a little longer than I expected. But yeah, so that's heaps, basically in a nutshell.
So you started with the number 2 to get the parent?
We started with the number 2, which is the rightmost in the array, and then you call the parent on that, and the parent is I div minus 1 divided by 2, and then once you get that parent, you start calling percolate down from the parent, and then keep it going left. And the parent always swaps. Well, first of all, you want to check if the parent is less than either of his children. If it's less than either one of them, then you swap whichever one was smaller. For a max heap, it's the exact same logic. It's just when swapping, you're looking for the greater one.
Okay, so you always start.
Yeah, yeah. Uh-huh. All right.
For the second array, the array in the middle,
Uh-huh.
it's actually, the 2 goes into the second index. You just didn't.
Yeah, it's just, yeah. Yeah, so the two kind of like swapped with, so the 2 was here, and yeah, it was just kind of like, it's a sloppy like intermediate stage.
Oh, okay. So
Yeah.
the original form is the first one?
This is the original, this is the final.
Okay.
Yeah, so this is here, let me just write final. All right, so let's move on to hash tables. So, runtime for hash tables. What's best case runtime for hash tables? Searching is, or insertion is order 1. Order 1. Average is order 1. Worst case is order n. Searching is, best case is order 1. Average is order 1. Worst case is order n. Deletion is order 1. Order 1. Also order n. All right. So briefly describe what a hash table is. So a hash table is basically just an array with a hash function. Array plus hash function. Where the hash function tells you what index to look at when searching or inserting or deleting, whatever you want. Yeah, it spits out a hash value, and that hash value, depending on the hash value, that's whatever you look at. What are the properties of a good hash function? Is that you basically have 3 main properties. Is that A, well, one, it must be deterministic. And then this is actually not a property of a good hash function. This is required. If it's not really a hash function if it's not deterministic. This is a required like property of a hash table. So 2, we have is that we have a wide distribution of data. Wide distribution meaning you don't want all your hash function values to be between 0 and 100. You want it you want it to be ideally between like 0 and 2 billion. You want a really wide range of values. Sorry? What about space complexity? No. So I mean wide distribution. So your hash function spits out values. So you don't want your hash function to always spit out like 0 to 100. You want it to be able to spit out values from 0 to 2 billion. It has nothing to do with space. It's just it's just it spits out a number. Okay. 3 is uniform distribution of data. Uniform distribution. So for example, even if your range is from 0 to 2 billion, you don't want your hash function to like 99% of the time give you like ranges from 50 to 60. You want it to be able to kind of like give you a uniform distribution of data. And what's the reason behind all this? Yeah, reduce collisions. Is that what you're gonna say? Yeah. Nice. So yeah, reduce collisions. And then what are the I just repeated the question. I didn't notice that. So what are the properties of a good hash table? Is that 1, at least half empty. So you always want your hash table to be at least half empty. At least half empty. And then you also want you want your hash function. Oh, sorry, you want your hash table to be a prime length.
So for number 1, it could also be like at most half full. Right?
Yes. Yeah, that's just basically multiply by -1, which is, but logic-wise. Anyways, you just negated the same thing. Now, so these 2 properties, they're not required. So they're requirements if you're using quadratic probing, which we'll get to soon, which we'll get to like just right after this. The requirements if you're using quadratic probing, they are preferences, like they're preferences if you're using linear probing or separate chaining. So yeah, just keep that in mind. If you're using quadratic probing, then it's a requirement. Here, let me rewrite that. For quadratic probing, because sorry? Yes, both of them are requirements for quadratic probing, because if you don't have them, then there is actually there's actually a high chance of you ending up in some kind of infinite loops when you're searching or deleting or inserting or any one of those. Okay, and then that's the same question. I'm not going to do it. I don't know why was that there. What's the main issue with hash tables and what are the different techniques we had to solve them? This is basically the collisions that we're talking about. So is at collisions. And then so the different techniques that we have to solve collisions or resolve collisions that we have our linear probing, and then 2 quadratic probing.
Do the runtimes displayed above apply to all the
Do the runtime? Yes. And then 3. So the question was, actually that's a good question. So the question was, do these runtimes apply to all 3 of the quadratic and linear probing and separate chaining? And the answer is yes, where the runtime could be any one of those if you're using separate chaining or any one of them. It applies to all of them. So yeah, and then last one is separate chaining. All right. Okay, next. Whoops, we did that. Now, applying hash table knowledge. So this is where we basically just use so this is the hash function right here. So the hash function that I gave you is it's probably not the best, but it's just something simple that I gave you guys just to kind of like get the idea of hash tables. Where is it? Oh yeah, here. So what you want to do for hash tables is that whatever number you're inserting, you want to put it into your hash function and see what number you get out. So for example, in our first case, I think I also changed some of the numbers here. So you might want to double check. The pre-updated worksheets had like different numbers because I was like talking about this earlier because the numbers I had like didn't have any collisions in them. So I changed the numbers so you could like get more collisions. Oh wait. No, they're not even here, so they're on my worksheet. So let's change these numbers. Let's put 34, 31, 34, 31, 77, 77, 26, 64, 39, 0, 7. All right, so these are the new values that we're going to be using because those values, they don't really result in that many collisions. So these have like more collisions and they're more interesting. So if you put 34 into your hash function here, 34. So you're going to multiply it by 3. 34 multiplied by 3, that's 136. And then so 136 plus half of 34, 37. That would give you something like 153, I think. Yeah. Wait. 34 multiplied by 3. Wait. Yeah, 34 multiplied by 3. No, that won't give you. That will give you 106. 106 plus. Yeah. No, I got. It's what? 102. 102. Yeah, 102, and then you add 17. Okay, yeah, that works. Okay, yeah, it works out. Okay. Yeah, so that's the thing. So if you put this into the hash function, it gives you. So 34 gives you, if you put it into the hash function, gives you 102. Oh, sorry, 119. Yes. And then you want to mod it by your table length. So now we need to decide what our table length is going to be. So how many? So here we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 elements. So using the 2 requirements or the 2 good properties of a hash table that we talked about earlier, what is the length of our table going to be? No, so that's what I was trying to get. So we want our table to be at least half empty. So we're going to double it first. So we have 8, so it's going to be at least 16. And then we want to get we get the nearest prime number, which is 17. So our table length is going to be 17, so we're going to mod by 17. Mod by 17. And then if we mod by 17, we get 0.
In this case, would you only mod when you go out of the bounds? Because like the hash function doesn't have a mod.
You still want to mod. Yeah, you always want to mod, even if you're not in bound. Like,
because it doesn't hurt to mod.
Exactly. Yeah. Why do we expand? When do we expand?
Why did you expand?
I didn't expand it. When did I expand it?
You made it from 8 to 17.
Oh, because, yeah, so why do we expand it? Because of the 2 properties that we had. So the properties was that it has to be at least half empty, right? So if we have 8, if we have 8 elements, so that means we must double it, because if you double it, then you have half of them have elements and half of them don't. Make sense? And then our next property was that you want it to be prime length, so you go to the nearest prime number, which is 17. What's up?
Is that a 109 or 119?
That's a 119. 119. All right, so sorry, we're gonna have to no questions, sorry. Yeah, later on. Okay, so 31 will give us 108. And then if you mod that by 17, that's gonna give you 6. And then 77 will give you 269. And then if you mod that by 17, you get 14. And then 26, if you do the same thing, it will give you 6. And then 64, if you do the same thing, it will give you 3. If you basically put into the hash function and mod it, it will give you 3. 39 will give you 0. Yeah, 39 will give you 0. And then 0 will give you 0. And then 7 will give you 7. All right, so those are basically, so these will be these numbers over here. These numbers are our indices. So if we use linear probing, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay. So if we use linear probing, we're going to start with putting our 34 at index 0. So 34 is going to go here. And then 31 is going to go at index 6. So 0, 1, 2, 3, 4, 5, 6. So 31 goes here. 77 goes at index 14. So we do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14 actually here. So here's 77. And then 26 goes to index 6. So 0, 1, 2, 3, 4, 5, 6. And then we have a collision. So since we have a collision, linear probing, what we're going to do is that you just keep on looking right after it, right next to it. So you keep on looking to the right. So since the 3 is taken, you're just going to look to the right of it right away. The right of it is empty, so we're going to put it there. So we put 26. And then 64 goes in index 3, 0, 1, 2, 0, 1, 2, 3. So 64 goes here. And then 39 goes in index 0. So 39 is going to go here. But since it's taken, it's another collision. So we're going to put it to the right. So 39 goes here. And then 0 also goes to 0. So we're going to do, this is taken. So that's taken. So you're going to look to the right. That's taken. You're going to look to the right again. You're going to keep on looking right until you hit a free space. So then you put the 0 there. And last one is 7. So it's going to be 0, 1, 2, 3, 4, 5, 6, 7. So there's 1 here. So we put it right next to it. So it's going to be 7. All right. So that's what it's going to look like with with linear probing. And then quadratic probing is a very similar idea or concept where, oh no, that's bad. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay. So quadratic probing is a very similar idea, but instead of looking right next to it, you keep on adding squares of like square of whatever number collision you're at. So the shortcut? It's not really a shortcut. It's just a different method. I'll talk about it anyways. So we're going to do the same thing where we're basically going to start at 34. So 34 goes in index 0. So 34. 31 goes in index 6. So it's going to be 0, 1, 2, 3, 4, 5, 6. So 31 goes here. 77 goes in index 14, sorry. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 77 goes there. 26 goes in index 6. So 26 goes here, so there's a collision. So we're going to look. So that was kind of like our first collision. So we're going to add 1 squared. So instead of looking right, I mean, so for the first collision, it doesn't really matter because you're looking right next to it because you're adding 1. So it will technically still go over here. So we put 26 there. And then 64 goes in index 3, so 0, 1, 2, 3, 64. 39 goes in index 0. So 39, so we're going to look here, there's a collision. So we're going to add 1 squared to 0. So it's going to be index 1. So 39 goes here. So now 0 also goes to index 0. So instead of adding, so we're going to look at index 0. So we're going to add, so we're going to look at 1. So we looked at 1, that's also taken. So instead of looking at 1, we're now going to add 2 squared, which is 4. So we're going to start back at 0. We're going to add 4. So we could do 0, 1, 2. Oh, sorry. 1, 2, 3, 4. And then it goes here. What goes there? 0. So then 7, it's 0, 1, 2, 3, 4, 5, 6, 7. So we look here. And then we add 1 squared. So 7 goes there. So like let's say if you want to add something else and it also maps to 0. So like let's say if you want to add 16. Let's say, for example, 16 also gives us 0. So we're going to start here, and then we're going to look to the next. It'll be 1, so that's taken. So now we're going to add 2 squared, which is 4. So it'll be 1, 2, 3, 4. That's also taken. So now we're going to add 3 squared, which is 9. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So 16 goes there. So you just keep adding squares from quadratic probing. So the last one is separate chaining. And separate chaining is just basically a bunch of queues. Yeah. So it's a bunch of queues. So you start with, so you could really start with however you want. So you could, like, let's say, for example, we start with like 10, with, I don't know, let's say, oh, whoops. Actually here, let's, yeah, so let's still do 17. So yeah, so let's do it like that. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, no, this is something like that. Anyways, so yeah, so now if we add them, we're going to start at the 34, so 34 goes 0, so here, so actually it's going to be a queue, so we're going to kind of like do an arrow, so it'll be 34, 34, and then we're going to add 31 to index 6, so 0, 1, 2, 3, 4, 5, 6. So 31 goes there. 31. And then 77 goes to index 14, so it's going to be 16, 15, 14, so like over here. So since they're queues. And then, what was I going to say? Yeah, 77 goes there. And then now 26 maps to, 26 also maps to 6. So, so the way 26 happens is that we're going to do a head insert. So the way that this is going to happen is that I mean, I can't really do this, so we're kind of going to like erase that. And then so our new queue is going to be 26 and then 31. What? Oh, what is it? Am I saying queues? Yeah, linked list, yes. Not a queue, because a queue you add at the back every time. Yes, a linked list. No, you don't sort it. You just always do a head insert. So before was it 31? So if you want to do a head insert, this is your head. So 26 is going to be your new head, and then you're going to look at 31. So 31 is going to like add up behind it. Yes, yes. Each one has a head pointer. Yes, it's a linked list. Each index is a linked list. And then so after that 6. So we do 3. So we put 64 and 3. So 0, 1, 2, 3. So 64 goes here. 64, and then we're going to add 39 and 0 into index 0. So this is going to look like this. So we're going to do 0, 39, and then it was, or sorry, 31. No, 39 and 31. All right. And then the last one is in index 7, which is 7. All right, so that's kind of like how it looks like with separate chaining. It's just a bunch of linked lists. So the expansion rule, oh man, I don't think I had any questions for expansion. Do I have, what's after this? Oh, math stuff, okay. So the way that expansion works in hash table is that once you get past that half full mark, you want to expand your hash table. You want to double it, and then you want to look to your nearest prime number. So in linked lists, you could basically keep on, or sorry, in separate chaining, you could basically keep on adding forever. So the way you want to do it is that you want to expand once your average list length reaches a certain limit. That's when you want to expand. All right. So math stuff. What? It's really whatever you want to be. Like it could be like 3, for example. 3 is usually like a good estimate. 3 or 4, 5. There's really no set limit. It's just whatever you want to be. So depending on how fast you want your hash table to be, or how fast you lookups. All right. So now base conversions. What time is it? Ooh, 6:17. Okay. I mean, 7:15. Okay, base conversions. All right. So let's do base conversions. So we're going from base 6 to base 10. So what does that going to look like? Multiply by what? Yes, so you're going to multiply by decreasing powers of 6 from left to right. So, or increasing from right to left, depending on how you think of it. So this is going to be, so starting from right to left, it's going to be 5 times 6 to the 0 plus 4 times 6 to the 1, 6 to the 1, plus 2 times 6 to the times 6 squared, plus 4 times 6 cubed. And then if you do that, you end up with 965. If you do the math with that. So next one is base 7. And then, so what do you do there? You keep on, you keep on dividing by 7 until you hit a quotient of 0. So you're going to do 917 divided by 7, that's equal to 131 remainder 0. And then 130, then you're going to take this number and then divide it by 7 again. So it's going to be 131 divided by 7. That's equal to 18 remainder 5.
How are you able to do this without a calculator?
I'm just really smart.
I mean, can you give us some tips on maybe we could chop off a certain...
I have the answers here.
I know, but like, if Sumeski gives us like...
He won't give you numbers, yeah. He won't give you numbers like that, don't worry. He'll give you numbers that are easy to work with.
That I can do in my head.
Yes, yes. Like he knows he's not testing you on your like arithmetic skills.
Oh.
He knows that. Yes, yes. Bases, yeah. He will ask you for 16. 16 is kind of the limit. He won't ask you for anything more than that. Okay. So, yeah. So that's going to be 8. So now we're going to take this number and divide it by 7. So 18 divided by 7 is equal to 2 remainder 4. And then we're going to take this 2. 2 divided by 7 is equal to 0 remainder 2. And that's when you stop. You stop when you hit the 0. So the final answer is going to go, you're going to go from bottom to top. So it's going to be 2, 4, 5, 0 in base 7. All right. So now then for question 3, what kind of rule are we going to use? Yeah, exactly. So we're going to kind of use that whole shortcut thing. Yeah. So what's the whole shortcut? That you're basically going to so since we're going from base 2 to base 8, so 8 is like a whole power of 2. It's 2 to the 3. So that means you are going to okay. So that means that you're going to take bits in pairs of 3. So you're going to look at the 0, 1, 0. 0, 1, 0 binary is just 2. So this is going to be 2. And then you're going to look at the 0, 1, 1. 0, 1, 1 in binary is 3. And then you're going to look at, 1, 2, 3, 4, 5, 6. Yeah, and then 1, 0 is also another 2. So I'll give you 2. So that's what your number is in base 8. You go from, yes, you go from, right to left. Yeah. Yeah, you can always pad it with zeros. Yeah. Yeah, okay, so 16, so next question is also the same you're going to use the same shortcut where it's 16 is a power, 16 is a power of 4 where it's 4 squared. So that means that each number in base 16 is going to be split up into 2 separate numbers. So this D, so D in base 10 is what?
13.
Is 13? Yeah, it's 13. So the kind of like the trick that I use that you start A with a closed fist and then you do B, C, D. So D is like 13. So yeah. So yeah, D is 13. So what's 13 in base 4? So 13 divided by 4 is equal to 3 remainder 1. 1 divided by 4 is equal to 0 remainder 1. 0. Wait, what? 3. It said 3 should be here, yes, because you take this number over here. So 3 divided by 0, yeah, that's 3. And then you can do it in reverse, so it's 30. So it's 31. So D in base 4 is 31. So you're going to do 31. And then 2. 2 in base 4 is what? It's still 2. It's just 2. And then A, what's A? A in base 10 is 2. A is 10 in base 10. But in base 4, what is it? It's going to be 22, which is 2. 2, 2, 2. And then you could use the same technique if you don't believe me, but you'll get 22. And then here we need to put a 0 2 because 2 in base 4 is 2, but we need to pad. We always do it 2 bits at a time, so we need to pad with that extra 0. So that's that in base 4. So how do we do something like from base 13 to base 9? Yeah, you use base 10 as kind of like an intermediate. So the way you convert 4, 5b into base 10 is that you multiply by increasing powers of 13. So b times it by 13. B is 11, so it's going to be 11 times 13 to the 0 plus 5 times 13 plus 4 times 13 squared. And then this is equal to 752. And then we want to go to base 9, so you basically just keep dividing 752 by 9. So 752 divided by 9 is equal to 83 remainder 5. And then 83 divided by 9 is equal to 9 remainder 2. And then 9 divided by 9 is equal to 1 remainder 0. And then 1 divided by 9 is equal to 0 remainder 1. So your final answer is going to be, you're going to start from, so you're going to start from bottom to top, which is going to be 1, 0, 2, 5, base 9. Oh, whoops, sorry. Yeah, now I can relate to professors now. Yeah, does that like kind of make sense? Hopefully it does, generally. Okay.
So for base 13, it only goes up to C?
Base 13 only goes up to C, which is 12. Yes, correct.
For number 4, what was that top part about, the top part?
Number 4? Oh, number 4, this was me basically converting D to base, to base 4.
But the point is you converted 16 to 10, then from 10 to 4?
Yes, just to know what, like, I mean, so if you've been doing this for a while, it's kind of like you could probably do it quicker, like in your head, but that's just for people who like are kind of like relatively new to this. You might have to do like that step, just to know what each individual, digit is. What? Use 10? What was 10? Yeah, A is 10, yes. Yeah. Yeah, A is 10 in decimal, but in base 4 it's going to be 2, 2. If you use the same technique. If you use this technique over here, you get 22. All right. So now this page. So for time's sake, I don't think we're going to do all of these. So we could do kind of like the most interesting ones, which are, for the first one, what's the first one going to be? Int max, which is what? 2 to 31 minus 1. They're 31 bits, so it's going to be 2 to 31 minus 1. And what's the next one going to be? -2, because so here we're using 2. Oh, actually, there's a question up top. I completely skipped it. So what system do we use to represent numbers in binary? It's 2's complement. And then make sure you know the spelling. Spelling is like a little important. It's not with an I, and it's with apostrophe. So 2's complement. And then the way we do that is just because math doesn't work with other systems. Math doesn't work, and then also they're going to be multiple definition of zeros.
Does it not have to do with the processor?
What do you mean?
Like, the reason why we use
No, it's mainly just because so if you use a sign magnitude, like we had the other one is sign magnitude. If you sign magnitude, like if you add -2 with 5, you're not going to get 3. You'll get like -7 or something. Like addition doesn't really work. So yeah, 2's complement, and then also you have multiple definitions. You're going to have like +0 and -0, which doesn't make sense. Okay, so this over here, if this were all ones, what number would that be? It would be what? If it's 2's complement. So if it's 2's complement, what are you?
31, negative 231 plus the first one.
So if this were all, so right now, if all these were ones, this number, so basically in 2's complement, this number over here represents negative 2 to the 31, right? So that's what that number represents, is 2's complement, that number over there. So that represents 2 to the 31. And then, now what does this represent over here, just a normal kind of like in a normal binary? That represents 2 to the 31. Now assuming that this was, now assume that this is a 1 for now. If it was a 1, it will be 2 to the 31 minus 1. So this will be negative 2 to the 31 plus 2 to the 31 minus 1. And then so this bit over here is missing. And what bit is that? That's the 2 to the 0. 2 to the 0, which is 1. So you subtract, so since that's a 0, so you're also going to subtract 1. So this cancels out with that, and then you end up with negative 2. So this is actually negative 2. And the next one is going to be, is the next one going to be positive or negative? It's positive because the first bit is a 0. And then, so since it's positive, you're going to look at all these bits. So if they were all 1s, what number would that be? It'd be what? No, keep the bit with the sign bit as 0. So it'll be 2 to the 31 minus 1. So that will be 2 to the 31 minus 1. And then what bits are we missing? We're missing 2 to the 0, missing 2 to the 2. So it'll be minus 2 to the 0, minus 2 to the 2. So that ends up being basically 2 to the 31 minus, so it's going to be minus 1, minus 1, so minus 6. What's up?
So like, there's a trick that I learned where you just like pretend everything is a 1, and then that's a negative 1. That's negative 1, and then like if you see a 0 anywhere, you just minus that. But what I don't understand is why that doesn't work with the first bullet. Like I did negative 1. So for the first bullet, negative 1, and then minus that 0, which is that 0 is supposed to be like 2 to the 31st.
That should be 2 to the,
Oh, it would be negative. So it would be negative 1 minus negative 2.
so you want to assume that it's, you want to assume, so your sign bit, which is your leftmost bit, that's going to be negative, that's either going to be, if it's 0, it's going to be 0, you're going to forget about it. If it's 1, it's going to be negative 2 to the 31. So then you're going to assume that all other bits other than that is 1, and then you start subtracting based on what you don't have.
So the leftmost bit is 0. It's just a positive of that.
No, if it's a 0, it's 0. If it's 1, it's negative 2 to the 31. All right, so I'm gonna have to move on. Sorry, like yeah. So if this were, so right now, so this is, yeah. So right now this is basically, so this is a 1, so this is gonna be negative 2 to the 31, and then if you're gonna assume that all these bits are 1, and then so then you're gonna add, if they were all 1, it will be 2 to the 31 minus 1, and then what bits are you missing? You're missing 2 to the 2, 2 to the 3, and 2 to the 5. So minus 2 to the 2, minus 2 to the 3, minus 2 to the 5. So if you do that, these two cancel out, and then you end up with minus 1, minus 4, which is minus 5, minus 8, minus 13, and then minus 32. I think that's minus 54 if my math is correct, but it's something like that. 45, sorry. And the other bits are basically the exact same process. I'm going to skip over those. It's the same process. Yeah, I'll post it. Yeah, I'll post all the solutions on the WordPress when we're done. So, what? Another what? Yes, yeah, I'll do. Yeah. I'll do that. Yeah, yes. Yeah, I'll have a copy of this, the same empty copy, and I have also a copy of the solutions. All right. So here, just to make life easier, I tried to make it in 8 bits. So we'll see if that actually confused people or not. So instead of 32, we're going to write them in 8 bits. So 20 in 8 bits, what is that going to look like? So you honestly, like the best, like the most secure way to do it is that just doing it like normal base conversion. So in base 10, that's going to be, so 20 divided by 2 is equal to 10 remainder 0. Then 10 divided by 2 is equal to 5 remainder 0. 5 divided by 2 is equal to 2 remainder 1. 2 divided by 2 is equal to 1 remainder 0. And then 1 divided by 2 is equal to 0 remainder 1. So your final answer for this is going to be 1, 0, 1, 0, 0. So it's going to be 1, 0. And then it's going to be 8 bits, so you want to pad with zeros until you get 8. What's up? What do you mean? What?
How we did it up here?
Yeah.
Like how we were subtracting plus.
Uh-huh.
I did it like that way.
Yeah, okay. If you get the right answers, then it doesn't matter. And I'm pretty sure that should work. So, okay, so if we do that, so you're going to end up with 1, 0, 1, 0, 0. And then, so we have 5 bits, and we want to pad until we get 8 bits. So we're going to pad until we get 8. So 0, 0, 0. Okay. So 45 is the exact same thing. Negative 1, what's negative 1 in 8 bits? It's all ones, yes. So negative 1 is always in all ones. So it's going to be 1, 1, 1, 1, 1, 1, 1, 1. And then 127 is basically the same thing as 20. It's just more division. So let's do a negative, like negative 55. So the way you do that is that you pretend it's a positive number. You pretend it's a positive number, so we're going to do it like normal, like 55 divided by 2 is equal to 27, remainder 1. 27 divided by 2 is equal to 13, remainder 1. 13 divided by 2 is equal to 6, remainder 1. 6 divided by 2 is equal to 3, remainder 0. 3 divided by 2 is equal to 1, remainder 1. And then 1 divided by 2 is equal to 0, remainder 1. So your final answer for a positive number is going to be, whoops, you can't see that, is going to be 1, 1, 0, 1, 1, 1. 1, 1, 0, 1, 1, 1. So we have 6 bits here, so we're going to pad with 2 zeros, so 0, 0. And now, so this kind of like the equation, and people who take in CDA are probably quite comfortable with this, is the equation to make it a negative number is, so you're going to do the not and then add 1. So you're going to do the unary operator, not n, then plus 1. So what does the unary operator do? It flips all the bits. So anything is 0, make it a 1. Anything that's a 1, make it a 0. So this is going to be 1, 1, 0, 0, 1, 0, 0, 0, and then you're going to add 1. So it would be 1, 1, 0, 0, 1, 0, 0, 1. So that's your final answer going to be, negative 55. 1, 1, 0, 0, 1, 0, 0, 1. And then the rest is basically all. So what's negative 128? That should also be quick. Yes, it'll be 1 and a bunch of zeros. All right. And then the rest is basically the same thing. It's just more math.
How did you add number 1?
Here. Then you add 1. Sorry. So you're talking about this part?
Oh, okay, I got it.
Yeah, you just add. So that's kind of like the equation. If you want to make so negative n is equal to
Bottom up.
where? Yeah. Yeah, I did read from the bottom up, but then I padded with zeros. Yeah. Yeah, so if you read from the bottom up, you have 6 numbers. So yeah, so then I padded with the left with zeros until you have 8 bits because you want it to be 8 bits. What's up?
If there was a 1 at the end, then you would just go to the next digit and carry it over there, right? The 1 over
Yes, yes. So like let's say if you had let's say if there was let's say there was a 1 here. If there was a 1 here, then you add, so 1 plus 1 in binary is a 0, and then you carry a 1, so that would be 0, and then the 1 would be here, so it would be like 1, 0. So yeah, yeah. Okay. Move on? Okay. So this is also a lot, so we might have to like skim through a couple. But yeah, so you start with some kind of like, it's just like a program, and then you start with c equals 5, and then you do a bunch of like one of these operators. So a left bit shift, what's the equivalent of doing a left bit shift? Yes, yeah, move to the left and pad with zeros on the right. Or in terms of multiplication, it's like multiplying by what? Multiplying by 2 to the power of whatever shifting by. Yeah, so if we're shifting by 2, then it's going to be the same thing as multiplying by 4. So this will basically be 20. C is equal to 20. So that'll print out 20. And then so if we print out 20 here, what's this going to print out? 5. Yes, that's a good note. So a left bit shift doesn't actually store it. You just do the left bit shift. So if you want to store it, you're going to have to say C is equal to C left bit shift 2. So its value is still going to be 5. It's not changed. Yes, you could have written C is equal to C2. And in that case, it would have been, then in that case, the value of C would have changed. It would have been 20. But since we didn't say C is equal to, since we didn't say C is equal to, then it didn't actually store the value. It's just, it did the mathematical operation. So 92 left bit shift 3. What does that do? What does left bit shifting do? Oh, sorry, right bit shifting. Sorry, it will be what? Do we subtract? We divide. Yeah, so it's dividing by 2 to the power 3. So if we do a right bit shift, it's basically dividing. So yeah, so that would be equal to 92 divided by 8, which would give you 12. All right. So what would this give you? So if we do, so right now we're saying C is equal to C left bit shift 31. Sorry? It's 92 divided by 2 to the power 3, which is 8. So 92 divided by 8 gives you 12.
12 times 8 is not 92.
Wait, is it 12? Oh wait, it's 11. Yeah, it's 11. Okay, yeah. All right, 11. So what's 5 in binary?
101.
It's just a bunch of zeros and 101. So if we left bit shift 101 31 times, what are we going to end up with? Sorry? Yes. So what were we saying, David?
It's like you go from the right or the left.
So we're left bit shifting to the left. So that means you take so an integer is 32 bits.
So the leftmost one
Yeah.
goes off.
It falls off.
Still have 0 and 1, correct?
Well, so even the 0 is going to fall off. So it's just going to be 1. It's just going to be 1 and a bunch of zeros. Yes. So zeros. Yeah. So it zeros out. So whenever you right bit shift, you pad with a 0, and since you're right bit shifting, since you're left bit shifting 31 times, all those bits are going to fall off except the rightmost one. And 5 is the rightmost one. So the rightmost one is going to end up at the 32nd bit, which is 2 to the 31. Int min, exactly. Negative 2 to 31, and then so this is basically the equation for taking the negative. So that will be equal to positive 2 to 31 plus. So but then you add 1. So it's just. So what happens if you? So here, wait. Oh, this is a little tricky. Okay, so if you do C is equal to, so first of all, we're changing the value of C right now. So then right now C is equal to int min, right? So if we take int min and we flip it, what do we get?
Int max.
We get int max.
Yeah.
So if we add 1 to int max, what do we get?
Int max plus 1.
Negative 1? So what does int max, here, I have like some scratch paper here. So int max looks like it's just 1. Int min is, int max is 0 and 1, 2, 3, 4. It's basically 31 ones, right? So if you add 1 to that, you're going to, so 1 plus 1 is 0. Then you're going to carry 1, 0. So it's going to, the one is going to be carried on all the way 0, 0, 0, and then 0. Then there's going to be 1 carried here, and then 1. So what's that? So what's that going to be? Negative, which is int min. So it's going to be. So it's still going to be. It's still going to be int min because because of the way integer overflow works. Because we basically kind of like flipped it to positive and then we overflowed and went back all the way to int min.
What's the little thing on the C next to the C?
What's what?
On next to the C, what is the little sign?
Oh, it's the knot. It's a weird knot. Yeah, so LaTeX has, yeah, it's a squiggly thing. That's the best squiggly thing I could get. So yeah, so this is still 2 to the 31.
Let's say you have like,
I'm really sorry, I can't like it's running out. So yeah, so okay. So if we print the knot of C, that's also going to be 2 to the 31. And then what's this? What's this number going to be? Or what base is it? It's hex 16. If you put a 0x in front of it, it's hex. If you put a 0 in front of it, what's the next one? That's octal. And then so you could do your normal base conversions. And then what does the unary do? Or not the unary, the AND. What? The what? Yeah. Yeah, so you look at each bit, and then 1 and 1 is 1. And then if you get anything 1 and 0, is it still 0? And then 0 and 1 is still a 0. All right. Yeah, so this is just like a bunch of like base conversions and like unary knot. I think it's relatively simple compared to like the other topics, so I think we should just move on. You put it into bits and then you do it? What?
Like 92 and 78.
Yes, you change. Yeah, you convert it into binary and then you do it. Yes. Yeah, you definitely want to convert into binary first. Okay, so now I think this is kind of like a little important. If you guys, I feel like if you guys understand this, then most of like bases like is quite solid. So the first question is, how many unique numbers can be represented with an unsigned int? 2 to the what? 31st. How many bits do we have in unsigned int? We have 32 bits. So what happened to the 32nd bit? No, but you said there are 32 bits, but you said 2 to the 31. Yeah. So it's 2 to the 32. That's how many unique numbers can be presented in an unsigned int. It's 2 to the 32 because there are 32 bits, and then each one of those bits could be on or off. So it's going to be basically multiplying by 32 times. 2 to the 32, how many unique numbers can be presented with a signed int? It's the same thing. It's the same thing, so it's the same thing, but so instead of going from 0 to 4 billion, so an unsigned could roughly go to 4 billion. Instead of going from 0 to 4 billion, a signed int goes from negative 2 billion to positive 2 billion. So you're still representing roughly 4 billion numbers, it's just that it's kind of like shifted. There's like some kind of like offset. Okay, so this is still the same thing, 2 to the 32. What's the largest number you could present with an unsigned int? 2 to the 32nd minus 1. Yes, 2 to the 32nd, because so in an unsigned int, you're using all 32 bits. So the largest number you could represent is 2 to the 32nd minus 1. What's the largest number you could what's the smallest number you could represent with an unsigned int? It's negative, or it's 0 with an unsigned int. So what's the difference between question 1? Why is there a difference between question 1 and question 3? Where why is this 2 to the 32 and why is this 2 to the 32 minus 1? Because of 0. Yeah, because we're trying to represent 0. Because of 0. And then there are a couple more questions over here. So, times it, 44. Okay, so what's the largest number that could represent with a signed int? That is 2 to the 31 minus 1. Because there's that one signed bit that we're kind of like not using, so it's not going towards like our positive numbers. And what's the smallest number that could be represented using a signed int? That's negative 2 to the 31st. What is the largest negative number that can be represented with a sign? Okay, so this is kind of like a little oxymoronic. The largest negative number you could represent. So this is actually negative 1 because, yeah, so just because negative 1 is kind of like the largest negative number you could represent. Yeah, so because negative 2 is less than negative 1. Okay, so technically the largest one is negative 1. So this is just kind of like generalizing it. How many unique numbers can be represented with n bits in base b? That's going to be b to the n. And then what's the highest number we can represent using n bits in base b, assuming it's unsigned, there's no 2's complement. So it'll be b to the n minus 1. All right. So bit masks. I would say we skip this part just because, yeah, so it's just basically a bunch of ands. And yeah, so we'll go on to backtracking. Okay, backtracking. So in 10 words or less, give a brief description of backtracking. Basically, backtracking is, in 10 words or less, it is recursion in a for loop. That's kind of like the easiest way to put it. Recursion in a for loop. And then what is the recipe for a typical backtracking algorithm is that, first of all, we want to start with, so one, we want to start with our base cases. And then two, after the base cases, you want to check if you're in a valid state. And this is optional because depending on the problem you're trying to solve in backtracking, you might be able to skip this step. So yeah, so check for valid or duplicate states. Or here, check for duplicate states. And this is optional. And then after that, you want to change your state. So, or sorry, yeah, three, you want to change your state. Change state. So changing state, so in terms of like the fox, goose, and the bag of beans, is like basically either sending the farmer down or sending some kind of doing some change to the state you're currently in. That's basically what I mean by change state. Or in terms of like like printing a try is that you move the whole null terminator thing and then putting a letter in it. Okay. So change state, and then 4, check if it's valid. And then this is also optional. And then 5, you're going to do your recursive descent. Recursive descent, and then 6 is going to be undo state change. Undo state change. All right. So that's basically like a typical algorithm for backtracking algorithm where you have these 3 steps. A couple of them are optional. You can roughly like interchange them depending on how you code it up, or like in different order. But that's kind of like a backbone for what it's going to look like. What? Undo. Undo state change. Yeah, it's just. I wrote state one more time. I don't know what happened there. So yeah, undo state change. So why is backtracking so powerful? So the best way that I think I would put like why is backtracking so powerful is that, so it's basically a way so it's that if you've been in a state that you've seen before, you're basically not making the same mistake twice. So if you've been in the state before, you basically just get out of it instead of going down that whole path again. Does that make sense? So yeah, so it definitely, it stops, so depending on how you put it up, it could be stops repeated, or prevents, not stops, prevents repeated calculation. Prevents repeated calculation, and B, yeah, B, it's just, I mean, yeah, that's honestly the only way. It's just mainly just prevents repeated calculation. So if you've seen a duplicate state, get out of it. There's no point of going there again because we've checked it before. And then what examples of backtracking they might have seen until now? So A, for Dr. Zumlowski classes, you guys have definitely seen the fox, goose, the bag of beans. And then for those in Dr. Mead's class, like the fox, goose, bag of beans, have you guys do you guys know like the classic problem of like trying to take like a fox, sheep, and some kind of like goose or something like that, and you're trying to cross over a river? Fox, goose, bag of beans? Yeah, that's basically what Dr. Zumlowski calls it. Yeah, that's the exact same thing. Yeah. And then you guys have probably also seen it for like printing all the combinations of a word or a string. Yeah, or printing a try, and then also printing. Actually, you could add that as kind of like another. Why is it powerful? Is that it goes through all possible states. Is that it's a really easy way to go through all possible states instead of having to like hard code stuff. So printing a try and then like combination of a string. The maze problem, yes, or yeah, maze, so we can also add that. All right. So the last question is what are the downsides for backtracking? Memory is a huge one. Is that it can be very, not only memory, you could also, so doing a recursive call is actually computationally expensive. It could be, sometimes it could be a lot slower. Like there are other solutions that would actually make it a lot faster. And we see that example in Fibonacci. If you do Fibonacci using incursion, it takes like ridiculously amount of time. If you like, once you go to like Fib of 45, like your computer basically starts like freaking out. And so A could be memory and time costly. Yeah, that's basically the main downside for it. It could be memory and time costly. And the CS2 teaser, I don't even know why I put that, but I was just, CS2 teaser, what are the different kinds of backtracking? This is something you can Google on your own time. You have your breadth first search, and then you also have your depth first search, which I'm not going to go to at all, but for those who are curious. Most of what you guys are doing is a depth first search. That's mainly what, yeah, that's most of what you guys are doing right now is a depth first search. Like printing a try, that's definitely depth first search. And what? Sorry? Yes, yeah, I'll upload the solutions, yes. What's up? Probably by tomorrow, sometime tomorrow. Yeah. All right, how much time do we have left? 8 minutes. Okay, 8 minutes. Go ham. What questions do you guys have? What's up?
So, like you said, for backtracking, you can check to see if you've already been in that state before.
Yeah.
In terms of code, like how would you check for that?
So the question was like in terms, so how in backtracking, how do you check for duplicate states? So are you in Dr. Mead or Dr. Zimlaski's class? Just out of curiosity. Zimlaski. Okay. So for example, in like the Fox goose, so sometimes that's why I put an optional around it because sometimes it doesn't really apply. Sometimes, like for example, like the sneaky rooks or sneaky queens, if you saw that using backtracking, there's really no duplicate states over there, so you don't have to worry about that. But so for something like the maze or like the fox goose or bag of beans, there are different ways you could do it. You could either store it in a string, or you could store it in a hash table. So like what you have, like let's say you store, like let's say if you do the fox goose or bag of beans, like let's say if you want to, let's say you have a string, and then you write, you put like letters for whoever's north of the river. So for example, like if you have your fox and your goose on north of the river, then that's going to be FG. So then you store FG in a hash table, and then whenever you do recursive descent, you search for FG in your hash table. If it is in the hash table, that means you've been in this state before. Does that make sense?
Yeah.
If it's not in the hash table, that means you've never been there.
If you get the same hash value, right, but then as FG, like let's just say because, right, but then you search through the string, and if they're not the same string, then it goes on to the next.
Yeah, it's basically collision. It's going to be normal collision resolution. Yeah, yeah.
You can also use bitmask.
Bitmask, yeah, you could also use bitmask. So you could have an all attributes, and then you could have like fox, goose, bag of beans. Farmer, fox, goose, bag of beans, and then one is like represent north of the river, and 0 represents south of the river. That's also one way you could do it, and then store that in a hash table or some array or something like that. It's up to you. But yeah, there are many different ways. Yeah. Any other questions before we wrap up and like?
I had a question on like
Which one?
like when you're doing this,
Mm-hmm.
Why would it be 230 to the 31st again?
Oh, that should be -1.
Oh, this is -1.
Yeah, 2 to the 31st -1.
Oh, that's fine.
Yeah, if I wrote 2 to the 31st, that's kind of like my mistake. So wait, let me see what they're right. So yes, this should be -1 over here. 2 to the 31st -1. Okay.
And
Good catch.
when you're, well, like, let's say you don't have like the bits.
Yes.
Say you didn't memorize the bits when you're inversing and then adding 1.
Yeah.
So like, how would you do it if you didn't? Like,
If you didn't inverse the bits and adding 1,
yeah.
say it one more time.
Like, you didn't go like bitwise.
Here, wait. So before you guys leave, if you guys, whoever, there weren't enough papers, but like the reviews, I would appreciate if you guys could fill out and just like leave it on tables. I'll pick them up. But yeah.
Says a bubble in the number.
Just ignore that. Yeah. Oh wait. So sorry. What was your question? Just one quickly.
If you didn't have the bits, if you didn't write out the bits and stuff like that, how could you do it like
The bit shift.
Yeah, if you didn't like bit shift.
So 31 2 to 31 is hard just because
Like
you're
you're inversing and then adding 1.
Yeah. What about it?
Yeah. Like what if you didn't bit shift the or like
If you did a bit shift.
yeah, like you're inversing all the bits and then you're adding 1.
Yeah.
So how would you do that like analytically?
So yeah. I mean, we'll talk later because I'm not really sure what you're trying to say in the other questions. What's up? Second to last one in this one. What is it's. So it's not 2 to the 31st plus 16. So negative 2 to the 31st, if you add 16 to it, that's definitely going to cause some kind of integer overflow. And then like a bunch of the ones would be a 0. So I'll say I think I put that just because like there are a lot of questions I put it just in case I didn't have enough time, but apparently like I put way too many questions. So those are one of the questions where I was just like thinking of just something extra. You're not required to know adding binary. That's like kind of like adding binary, except maybe for 1. Adding 16 in binary, you're not required to know that. So yeah, don't worry too much about that. And plus, yeah, forget that one. As I said, there are a lot of questions where I didn't know how long this was going to take. It took a lot longer than I thought. So yeah. Any other questions? Well, we're kind of like, what time is it?
Question.
What? What's up?
For the tilde, isn't the formula negative of the, you add 1 and then you take the negative?
So the formula is negative n is equal to tilde n plus 1. So tilde n is equal to minus n plus 1. So yes, that's kind of like the formula.
Negative n? Oh, you can just like plug that in. Okay.
Yeah, so you take whatever n is, add 1 to it, take negative n.
Oh, that's true. Like negative n is equal to that. That's the universally true.
Yes, yes. All right. Well, thank you guys for coming. What? I'll just skip them on the table. I'll pick them up. Yeah. Thank you guys for coming. I've really enjoyed like teaching you guys this semester. And then good luck on your exam. And then hopefully I'll see you guys in CS2 or something like that. Yeah. Yeah, definitely, dude. That was good.